Great. Yeah, thanks very much to the organizers for the invitation to speak. So today I want to tell you about work done in collaboration with this group of people and not published, on the archive. We don't publish papers anymore in these papers. And I particularly want to call out Benedikt Plake, who's here in the conference and here for the next month, and Tibor Rakowski, who all of you know. Okay, so the theme of this conference is the close connection between many-body physics and between information and computation. And to me, this will mean the close connection between ordered phases of matter and error-correcting codes. Okay, so in particular, what we've come to appreciate through many examples is that when we have an ordered phase of matter, a gapped ordered phase of matter, this is characterized by a ground state degeneracy, which is usually robust. Okay, so we have 2 to the k degenerate ground states, say. If this is a non-trivial ordered phase of matter, then these ground states are going to be macroscopically distinct. They're going to look very different. To connect between these ground states, we need to act with some operator, which we'll call D. And this operator D scales with system size in some way if these states are macroscopically distinct. Okay, and of course the key insight is that we can use these features of the spectrum of some Hamiltonian to also describe, specifically the ground state subspace, to also describe a code with parameters n, k, and d, where n is the number of physical qubits, k is the number of logical or encoded qubits, and d is the code distance. Okay, so 2 paradigmatic examples of this is, of course, when our many-body ordered phase of matter is something that is a phase with spontaneous symmetry breaking, for example, the Ising model, then this can be used to robustly encode classical memory. For instance, in the repetition code, the 0 and 1 states can be thought of as the all-up and all-down states of an Ising magnet. And, of course, if you want to encode quantum memory or quantum bits, then that's associated with topological order, which can also be understood as a type of spontaneous symmetry breaking, but of higher form symmetries. Okay, but you know, the conference is embedded within a larger program, which is called Noise Robust Phases of Matter. So we care not just about encoding information in ground states, but we also care about memory, right? How is that information going to remain stable? And really, fundamentally, memory, to preserve information in the code space, is a dynamical process, and in particular, it's a non-ergodic dynamical process because we want to keep information in a tiny subspace of the full available Hilbert space or configuration space in the presence of noise. Okay, and the type of memory that we can get cares fundamentally about the nature, not just about the ground space, which we use to encode information, but also by the nature of excitations in the Hamiltonian. Okay, so there are 2 kind of broad classes of memory that people usually talk about. The first can be thought of as active memory or active error correction, where by active I'll mean a dynamical process that breaks detail balance. Okay, so for instance, you can have some code some code state that's encoded, but there's noise in the system, and you want to remain in the code space. So you might make measurements to detect where your errors or syndromes are, and then you process this syndrome data on a classical computer, and you act with some corrective unitary. Okay, so this processing could be local or non-local, but the key point is that to call it active, it has to break detail balance. Okay, and this is, of course, the paradigm for how the toric code in 2 dimensions protects information. You want to take entropy away from the system. Noise is adding entropy, and the way we take that entropy away is by processing information, which is making measurements and doing corrective unitaries. For this talk, I'll be interested much more in passive memories or systems that can preserve information while under dynamics that obey detail balance. Okay, so now what I have in mind is, again, some Hamiltonian system. But now, just by coupling my Hamiltonian system to a cold enough reservoir or bath and going away for an arbitrarily long amount of time, I should be able to come back and recover the information that I encoded. Okay, and this paradigm for preserving memory is generally associated with thermally stable order. Okay, so just to illustrate this with some simple examples, okay, familiar examples. We know that if you just want to protect classical information via spontaneous symmetry breaking, then if we encode this in the one-dimensional repetition code, okay, or the one-dimensional Ising model, we know that the 1D Ising model does not have a finite temperature ordered phase. The excitations, the domain walls of this 1D Ising model are point-like and deconfined, okay, so you can, once you make a pair of domain walls, you can separate them arbitrarily far at no additional energy cost. So there's no finite temperature ordered phase, entropy always wins over energy. And now in order to protect information in this 1D repetition code, we need to do active error correction, okay? This is in contrast to the 2D Ising model or repetition code, in which case, because of this 2D geometry, there are many local redundancies between my Ising checks. The product of Ising checks around any one plaquette is the identity. These local relations or these local constraints force my domain walls to be extended or loop-like. This leads to thermally stable symmetry breaking order. We know the 2D Ising model has a finite TC, and this can be used to passively encode classical memory. The quantum analog of these two paradigms is, of course, the two-dimensional toric code, which, like the 1D Ising model, has point-like deconfined excitations and no topological order at any finite temperature. So error correction in this model is active. And this is in contrast to the four-dimensional toric code, in which my excitations form extended loops. There is stable topological order at finite temperature, and we can do passive error correction, okay? And these two problems, even though they look quite distinct, as has been discussed many times in this conference already, there's a deep relationship between these problems through this formalism of product constructions, and indeed the nature of excitations in the toric code is very much derived from the nature of excitations in the corresponding Ising models, and the self-correction properties are likewise, or the error correction properties are likewise morally thought to follow the same kind of reasonings, okay? So good. So this is kind of like almost every code that we think about in finite dimensions. At least I like to put in one of these two boxes, and that's roughly true modulo details, okay? But a central theme of this conference, this is from the conference description, is recent theoretical work has seen constructions of novel families of quantum codes in non-local geometries that challenge conventional notions of phases of matter, right? And also that these developments raise new challenges and scientific opportunities in quantum many-body physics when describing the properties and evolutions of encoded quantum matter. Okay, so this is going to be the focus of my talk, these types of unconventional phases and the new and unconventional insights that they give into many-body physics. So this is inspired by this new family of codes, so-called good quantum LDPC codes. Okay, so you've heard a lot about LDPC codes, so I'll be very brief. Okay, LDPC just means low density parity check. These codes are finite connectivity models, which just means that every bit or qubit is acted upon by finitely many checks, and every check is only part of finitely many bits or qubits. Good codes have the code rate k and the code distance d, both scaling proportionally to n. And Bravi, Polin, and Turhal showed in 2010 that in order to get such good codes, while remaining LDPC, we actually need to put our codes on expander graphs. Okay, these expander graphs are families of graphs in which roughly have the property that boundaries or surface areas are proportional to the volume. Okay, and what does that mean? That means that if I cut out any subset S of sites from this graph, as long as the size of that subset is less than or equal to half the total number of sites in the problem, then the neighborhood of that set, or the number of edges that connects that set to its complement, scales proportionally to the size of the set itself. Okay, so this is not true in any finite dimensions, where we know that boundaries scale parametrically weaker than volumes. Okay, so these LDPC codes are local on these types of graphs, And while classical examples of these LDPC codes have been around for many decades, the quantum versions are relatively, these good LDPC codes are a relatively recent development, okay? And just as from a physics point of view, to give you a sense of what these models look like, the proofs themselves of these good LDPC codes involve fairly complicated models, but you know, morally, there's a pretty simple picture. Imagine that you have some expander graph of this form, and imagine that you have, for the classical version, you just have some kind of generalized Ising model, which is local on this, okay? So for instance, I could put bits on all the edges, and then every interaction lives on a vertex and acts on the bits surrounding that vertex, and these can be like few body, you know, Ising-like interactions. They don't have to be two body, but that's morally what it is, okay? I drew a picture of this kind of locally tree-like geometry, but actually another very physical class of these graphs are hyperbolic tessellations, which are also of interest in many other contexts. Okay, so now to make quantum codes, we need some version of like higher dimensional expander graphs. Okay, it's hard to draw. This is like a picture Nico drew, which is supposed to like, I don't know, there's like some book-like structure. There's basically plaquettes. Imagine taking a product of these two graphs. Like, you know, if you take a product of two circles, you get a torus. That's easy to visualize. Now imagine taking a product of this crazy graph. You get something that locally looks like that. But anyway, you can now take this graph and put down some generalized toric code on it, which again has some few body X and Z interactions, which are local on this crazy graph, and all the checks commute with each other, okay? So the underlying question is, what is the physics of these LDPC codes? Okay, so other types of error correcting codes, such as the toric code, we understand in terms of physical properties. Can we similarly associate these types of Hamiltonians, which are unconventional due to the geometry in which they live, but also have various nice properties because they're local on these geometries? Okay, so there is a sense in which they are sensible many-body Hamiltonians. What kind of physics do they correspond to? Do they correspond to stable phases of matter? Are there aspects about these models which can be understood in the language of topology and gauge theories? Okay, so we've been trying to understand and ask these questions for the last few years. And I'll say that one aspect of the ground state physics that we've addressed is actually quite striking, okay? So this was in these two papers here by our group and Andy Lucas's, where, you know, in these models, the code rate is proportional to system size, which means, and the number of ground states is 2 to the k, or exponentially many in system size number of ground states. And what we showed is that if you actually come in and you act with perturbations that are weak but local on this graph, then much like results that exist for finite dimensional Euclidean systems by Matt Hastings and collaborators, we can show that the gap remains open and the ground state degeneracy is split by some amount that's exponentially small in system size. So this ground state degeneracy is robust. Okay, and this is also pretty unusual from the point of view of something like the third law of thermodynamics, because this is an extensive ground state entropy that's robust to perturbations. Okay, so that this also lends credence that we should think of these models as genuine phases, because at least this property of gap and ground state degeneracy is stable to perturbations. Okay, so now I want to turn to asking, what is the nature of memory in these expander LDPC codes? Okay, and here I want to start with a puzzle. Okay, so I started by telling you that we tend to think of memory as coming from finite temperature, thermally stable order. However, on these expander graphs, in these expander codes, there are many known classical and quantum expander LDPC codes that do have robust passive memory with local decoders. However, if you look at the partition function of these models when viewed as Hamiltonians, then that partition function looks analytic at all temperatures. Okay, so there isn't a conventional thermodynamic phase transition into some kind of low temperature ordered phase. And the way to understand it is that many of these models have no or few redundancies in their checks, which is just another way of saying that every check is independent, like in a 1D Ising model with open boundary conditions. So if you do a Kramer's one-year transformation, you can write a Hamiltonian purely in terms of the checks, each of which is independent. This just looks like a trivial paramagnet with a perfectly analytic partition function. Okay, so the tension is, how do we reconcile this analytic partition function, which naively shows no TC, with the fact that this does have a robust passive memory. Okay, and this puzzle was highlighted recently in this paper from Andy Lucas's group. So to answer this question, I'm going to start by first just giving you a summary of our results. Okay, so the main result that I want to present is that there is a new type of phase of matter, what we call a topological quantum spin glass, and this new type of phase of matter is what underlies memory in these quantum LDPC codes. Okay, so as the name suggests, this phase combines features of spin glass physics with features of topological order. In particular, the model has robust long-range entanglement and quantum memory at finite temperatures, but this exists within a complex free energy landscape with many global and local minima separated by extensive barriers, and this type of landscape underlies a lot of the physics of this phase. Okay, so already from a many-body physics perspective, these codes have revealed kind of an interesting new phase of matter. Okay, where spin glasses separately have been a focus of much attention, but here, these squiggly lines are supposed to denote that the nature of the states that lie at the bottom of these wells is very different from what you usually think about in spin glasses, and these states are highly entangled and topological in some way. Okay, so it's already interesting as a phase of matter, but also, of course, the reason we arrived at this is because we were thinking about the physics of these LDPC codes. So it's certainly also interesting from the point of view of error correction. And in particular, it furnishes a new mechanism for passive quantum memory, which goes beyond spontaneous symmetry breaking. Okay, in this case, spontaneous symmetry breaking of higher form symmetries. What it also does is it makes us rethink our understanding of the code rate, which is how many encoded qubits we have. Usually this is just associated with the ground state degeneracy, but actually in these models, there are many embedded quantum memories including in excited states. Okay, so there's actually the code itself contains many copies of a quantum memory in a way that I will describe. And what I found actually pretty exciting is that we were able to rigorously prove the existence of this phase. Okay, rigorously prove the existence of spin glass order and this topological feature. And rigorous results in spin glasses, even on classical spin glasses, which have been around for 40 years, are actually very rare. And the work on this often ends up looking extremely convoluted, extremely technical. But we were actually able to use these insights from codes to make progress also on long-standing problems in classical spin glasses. And in particular, to the best of our knowledge, we furnished the first rigorous proof of spin glass order in a model with finite connectivity. Okay, so finite connectivity meaning this LDPC property. And the proof actually did not rely on any of this complex formalism of replica symmetry breaking and so on that makes a lot of the conventional analysis in spin glasses quite difficult to parse. But instead, we just used code theoretic properties and combinatorics, and there's a very physical origin for where the spin glass order comes from. Okay, and en route, we needed this key technical result, which is a quantum generalization of this well-known bottleneck theorem, which exists for classical Markov chains. This is what we used in order to define and prove spin glass order. And independently, this helps us think about defining thermal phases at finite temperature and their stability and phases at open quantum systems. This perspective through bottlenecks gives us a new angle on asking those questions. And this helps us bound the performance of various quantum Gibbs samplers that we've heard about in various talks, such as from Anthony. Okay. All right. So any questions in the setting before I delve in? Okay, so, all right, so now I want to start by presenting a slightly more formal view of passive memory, particularly from the point of view of this bottleneck theorem, okay? So, again, let's go back to classical physics for a moment, okay? So, to understand passive memory in the 2D Ising model, the way we think about it as physicists is that there's a thermodynamic phase transition at some Tc, and there's two symmetry broken equilibrium states, which we'll call rho up and rho down. This is the mostly up and mostly down states, okay? And these states are separated by some macroscopic free energy barrier. The global Gibbs state, the Gibbs state, e to the minus beta h, can be written as some combination of rho up and rho down, okay? And in particular, the reason this has a memory is that if I start in something like the all up state, and I do detailed balance obeying Glauber dynamics at some finite temperature, then I'll quickly relax to rho up and then stay there for some time that diverges exponentially with some power of the system size before I mix and relax to this global Gibbs state, okay? And there's actually a formal sense in which rho up and rho down should be thought of as Gibbs states in their own right, okay? And a language that you can use is that the Gibbs state of the system ceases to be unique for temperatures less than Tc, okay? And there's a lot of work in classical stat mech in formalizing exactly what we mean by having non-unique Gibbs states. There's various formalisms like this DLR perspective or the Pyrrol's perspective for talking about this, okay? The thing that will be most relevant for us is a dynamical perspective on non-uniqueness of Gibbs states, which follows from the bottleneck theorem, okay? And this tries to quantify exactly what I just said intuitively, which is that if you start in a state which is mostly up, you'll quickly relax to rho up and stay there for some very, very long period of time, okay? And one way to understand that is to look at the global Gibbs state, in this case, rho Gibbs, okay? And you ask, does it have this structure where the dominantly the Gibbs state has weight on these two components in configuration space, so these two subsets in configuration space, which I'm calling omega up and omega down. These can be like large positive and large negative magnetization. And then in the Gibbs state, between these two components, there's actually a region of configuration space with very low weight, separating these, okay? So these could be, for instance, states with very low magnetization, okay? Now, if I start in one of these components, let's say in the all-up state, and I start running local dynamics, the point is that I have to go through this no man's land, this bottleneck region, before I can get to the other state, okay? And this no man's land has very low weight in the Gibbs state, so this means that if I start here, I'll hang out here for a very, very long period of time. And this can be formalized within this bottleneck framework, where you can write down a bottleneck ratio, which is the ratio of the weight of the Gibbs state on this red kind of bottleneck region divided by the component, okay? So you're asking about the relative weight. Because the Gibbs state is e to the minus beta f, this ratio quantifies a free energy barrier, because this makes this notion very quantitative. And then it tells you that the memory time of staying in this up component diverges as this bottleneck ratio, which for the Ising model scales exponentially with the linear size L, okay? So just by looking at the global steady state, you can do this decomposition into different components, and then by looking at the relative weight of these components with some kind of color region that's surrounding them, you can quantify again what the free energy barrier in the system is and what you expect the lifetime of these components to be. Yeah? Not necessarily, right? Like, if you just look at the Gibbs state here, it just has weight that is peaked on these two positive and negative magnetization components, and these just look like nice Gaussians, and then you just have this no man's land in the middle with very little weight. Yeah. Okay, so So now, if we come back to what we mean by passive memory that encodes non-trivial classical or quantum information, this is encoded in the structure of Gibbs states. Okay, so each of these components with diverging lifetime can be thought of as a Gibbs state in its own right. Okay, so I'll sometimes call them Gibbs state components or just Gibbs states. Okay, and the nature of memory is encoded in the structure of these Gibbs states. So if you have a classical memory, then any state, any steady state, okay, can be parameterized by this number p and can be written, if it encodes 1 bit, any steady state can be written as p times rho up plus 1 minus p times rho down. Okay, you can choose p to be what you want, but this is a two-dimensional vector, p, 1 minus p, 1 bit of classical information, which is encoded forever. Okay, any state that you prepare like this will remain stable. Okay. If you want a quantum memory, then the nature of your steady state subspace looks qualitatively different. Okay, so this gets to the type of things that Tiago was bringing up in his talk. Okay, there's actually structure theorems in math that tell you that, like, for a quantum memory parameterized by say this vector alpha, every steady state has the form that it can be written as this tensor product between this 2 by 2 density matrix, if I'm talking about a qubit. This encodes the state of the logical qubit, and a syndrome, the rest of this can be thought of as a syndrome density matrix, which is the same, which is independent of alpha and the same for all Gibbs states. Okay, so every choice of alpha defines one of these metastable states that Tiago and Anthony mentioned. Okay, so more generally, if I have many bits or qubits, then I can write rho alpha as this sum over all of these different Gibbs state components, 2 to the k of them, and this rho alpha for a quantum case is written as this tensor product, where sigma does not depend on alpha, but mu alpha is this 2 to the k by 2 to the k density matrix, which is the state of my encoded logical information. Okay, and I'll say that the rigorous results on these structure theorems are about exact steady states. So if you have exact steady states with this kind of degeneracy, then you can make these statements. Something that we're working on, but which is looking quite promising, is generalizing these structure theorems to these asymptotic steady states where the Gibbs state component does have some lifetime, but that lifetime diverges with system size. Okay, so now let me move on and spend a few minutes telling you about spin glass order, which is a qualitatively distinct physical mechanism for obtaining passive memory. Okay, so when you think of spin glass order, the first image that might come to your mind is some complex landscape with many different global and local minima. Okay, there's some spin configuration at the bottom of each of these wells, and you know, this type of picture of this complex landscape is most clearly being established for models in these very non-local geometries, or these mean field models, okay, where suppose you have some all-to-all connected system with random positive and negative couplings. This is known to have spin glass orders, like the Sherrington-Kirkpatrick model. Okay. Now these local minima are associated with equilibrium states, okay, with asymptotically diverging lifetimes below some transition temperature, which is called the glass transition temperature. But crucially, this is a dynamical memory transition, which need not be accompanied by any thermodynamic phase transition in the partition function. Okay, so the partition function can look completely analytic through this TG. And this is well understood in the study of classical glasses. And the reason this is, again, conceptually very distinct from spontaneous symmetry breaking is that most of these minima are not related by symmetries in the problem, and there are in fact many more local minima than global minima. Okay, within the bottleneck picture, you can think of each of these wells as encoding each of these wells as being associated with some bottlenecked subspace. Okay. So formally, if you want to define spin glasses, okay, it's actually another nice feature of this bottleneck perspective is that it gives a very clean definition of spin glasses, which we can prove. So let me do that for you here. Okay, so In the most general case, I described the 2D Ising model for you, where there are the two Gibbs state components related by the action of Ising symmetry. In the most general case, you can have many, many, many components, or many Gibbs states, and these Gibbs states need not be structurally similar, they need not be related by the action of any symmetries in the problem, okay? Now you can take your global Gibbs state, e to the minus beta h, and write it as a sum of these many, many bottlenecked components, okay, with these weights wi. And these weights basically have to sum to 1 up to some tiny error. And now you can characterize the complexity of this decomposition by computing various entropies of this decomposition. Okay, so for instance, you might be interested in computing the Shannon entropy of this distribution, which tells you how many relevant components are there. Or you could look at the min entropy, which is basically the weight of the largest component. Okay? And then you can define spin glass order via these two properties here. The first is shattering, which basically tells us that no single Gibbs state component carries more than an exponentially small fraction of the total weight. Okay, so there's at least exponentially many components that are present. And this means that the minimum configurational entropy density is positive. Of course, if I just had a code with finite code rate or exponentially many ground states, and each of those had some stable minima, then I would already get exponentially many Gibbs states, okay? But to call it a glass rather than a phase with spontaneous symmetry breaking, I need this additional feature of incongruence, which is telling me that there are many, many, many more Gibbs states at finite temperature as compared to the ground state. Okay, so the entropy, this configurational entropy as a function of temperature there's a larger entropy density at finite temperature compared to what we have at zero temperature. So there are many more local minima than global minima, and in fact there's exponentially many more local minima than global minima. Okay, so using this definition and various properties of expander codes, we were able to prove spin glass order, that is shattering and incongruence, in classical spin glasses on these sparse graphs, which stands in contrast to all graphs where rigorous results are known, and finite connectivity graphs in finite dimensions, in which even after 40 years there isn't any prevailing consensus on what the nature of spin glass order looks like. Okay, but we were able to give a rigorous proof in this setting here. And crucially, when people talk about spin glass order in this setting, they invoke this framework of replica symmetry breaking, and these replicas are loosely or heuristically associated with these Gibbs state components, but the correspondence is indirect and subtle, but here we can kind of directly talk about what the components are and how they arise. Okay, so just give me 2 more minutes. So now I want to move on to talking about memories, right? And in the classical setting, I have all of these stable minima. So the states that are at the bottom of these minimas can be thought of as stable configurations, right? Like if I have some noise that corrupts things, I can always cool my system back down and find a minimum again, okay? I should actually say also that the fact that I have this large configurational entropy is also the reason why cooling spin glasses to find the ground state fails, okay, this annealing property, because then you tend to get stuck in these local minima. But if you start in one of these minima and you corrupt the state a little bit, you can find your way back. So in general, if I have 2 to the k stable minima, I can encode k logical bits in the system, okay? And the question is, can we encode quantum memory in a similar way? Okay, usually when people talk about quantum spin glasses, they have in mind a classical spin glass and a transverse field, but just like you can't take the 2D Ising model and add a transverse field to it and make a quantum memory, you need some fundamentally different way to make it topological. Likewise, to make this glass into a quantum memory, we need this new type of glass, which is what we call this topological quantum spin glass. So I'll just define this for you and point out that we prove the existence of these glasses in various expander codes. Okay, so what characterizes this phase? First, we have shattering and incongruence, what I just described to you, which is a feature of the classical complexity of the free energy landscape. So there's many global and local minima. But But now, okay, so this is the structure. K is proportional to n. So I have 2 to the k ground states, okay? But now within a given logical sector, I have exactly one ground state, but I have many, 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 in fact, exponentially many local minima, which are each stable and which are each very, very far from the ground state in a way that you can make precise, okay? And then what makes this topological? Well, each minimum hosts a stable Gibbs state, but this Gibbs state has long-range entanglement, okay, which means that this Gibbs state does not have any decomposition into pure states, where the pure states can be written as purely short-range entangled states, where short-range entangled states are obtained by a finite depth circuit starting from product states. Okay, so there's each of these Gibbs states has long-range entanglement in the sense defined by Hastings. And finally, there are many emergent or embedded quantum memories in this problem. So I can take these ground states, okay, which are denoted in dark blue, and make a quantum memory from that. But then I can also take this state at this blue well associated with this local minimum and all of its copies, and I can make a quantum memory that's a separate quantum memory that is embedded within the system. Okay, so I don't have time to get into proofs, but they're very transparent. I'm happy to talk to you after it, and they come from this feature of code expansion, which gives me large energy barriers. Okay, so that's the key insight. I have extensive energy barriers in classical codes for around ground states. I can use those to get extensive free energy barriers around ground states, and then also to get many, many more stable local minima with extensive barriers just by a simple counting argument, okay? But everything follows from the structure of energy barriers and free energy barriers, which can be derived in just that much algebra, okay? And then if you want to get to quantum LDPC codes, we use product constructions. Things become more subtle because you often have barriers that are sub-extensive and not extensive, but we can nevertheless deal with it and still prove bottlenecks and free energy barriers. This upshot is just, we go from energy barriers in classical codes to energy barriers in quantum codes, which might be sub-extensive, but nevertheless can be used to prove bottlenecks, and the structure of these energy barriers comes purely from code expansion. Okay, so it's very, very transparent. And then the type of memory that the structure of these Gibbs states encodes is a hybrid memory between quantum and classical, where you can think of the classical piece as picking out which of these embedded memories you want to talk about, and then that memory has the structure that I described to you earlier. Okay, so that's my summary, that there's a lot of work on thinking about new directions in many-body physics and open quantum systems and expander graphs, and this topological quantum spin glass is one illustration of this. Okay. Yes.
Yeah, thanks, Vedika, for a very nice, clear talk. Questions? Here you go.
Yeah, thanks for a nice talk. Could you briefly comment on how to make this work for non-commuting settings?
Yeah. So this bottleneck theorem, this quantum bottleneck theorem that we proved, that's for non-commuting Hamiltonians, and there you can start with something like a stabilizer Hamiltonian for a good quantum code, for instance. And then in the case, so there you have large barriers, and you can prove these bottlenecks, large energy barriers. But then you can show that you can perturb those models, and the bottlenecks remain stable because they were derived in these cases from these large barriers. So that, so there is a notion of stability that you can prove, and the quantum bottleneck theorem does not rely on commuting Hamiltonians.
Yeah. So for classical spin glass order, we need some sort of frustration quench disorder in the Hamiltonians, right?
No, so that's actually a striking feature here. So this is not new to us. This was already appreciated in the classical spin glass community, that you can think of these as more akin to geometrical glasses, where it's this geometry that's giving you the frustration of having these many, many wells. But we're thinking about a linear code, so every term is positive and constant. Okay. Yeah.
In classical theory, such codes usually correspond to larger stability than those embedded in lower dimensions. So somehow you pay more energy to create some amount of noise of errors.
Yes.
So would you expect this to be more stable as a memory than 4D code?
Yes, exactly. Indeed, because and that can be quantified, and in fact, like that's what makes the proof of stability, the other proof of stability that I was just mentioning, very transparent. So the feature that's true about these problems is that they have a property called linear confinement. So in the classical case, you have a linear energy barrier, so an energy barrier that grows as that has this feature where as you flip some bits, as long as the number of flipped bits is less than delta of n, the energy barrier scales proportionally to the number of flipped bits. So this is linear barrier. By the time you get to quantum codes, you still have this linear barrier structure, but it can get cut off at some value, which it's a linear barrier, but it only extends to delta of n, and delta of n could be square root of n. So this is qualitatively different from a square root of n barrier out to a linear distance.
That's LTC in the classical.
It's not LTC, because LTC would tell you that you can go to half the code distance and there's no other minima.
LTC up to that.
Up to that. But in general, if it was LTC, it would actually LTC requires lots of local redundancies, and that would most likely be thermally stable. But here, the fact that I have all of these local minima all over the place means that it's not an LTC in either classical or quantum. Yeah. But it's this linear barriers as opposed to a square root barrier that makes it more stable. Yeah.
Let me ask a question on the quantum many-body perspective on the topology. When you say there's long-range entanglement,
yes.
For conventional codes, we identify that over a boundary law and a subleading correction.
Yes.
So this is happening here as well?
So here there's no distinction between surface area and volume. So no, even if you have things like Wilson loops at some like exactly solvable point, you can't at the stabilizer point, at the ground state, they'll have a one law, but away from that, you can't distinguish between area and volume. So what the order parameters for these models should be, in spin glasses, people talk about these point to set correlation functions, but already trying to think in that language for finite dimensional topological phases is quite challenging in terms of these Gibbs states and DLR prescriptions. So what the order parameters should be, there are analogs of the logical operators, which are like the Wilson loops, not loops, but Wilson nets. But exactly what the order parameters should be is still quite subtle. Yeah, okay. I don't know the answer. Yeah.
For some of your results, you mentioned that you need to have no redundancies. Is it a problem, is it a feature of the proof, or is it something that you think will go wrong?
Oh, good. It's a feature of the proof. I think as long as we have sub-extensively many redundancies, we should definitely be safe. By the time we get to extensively many redundancies, it shouldn't be a problem for memory, because it just takes you from this glass to something with actual stable order. But then proving spin glass order with these many local minima could be quite challenging, or may not even exist. Yeah.
Got it. Thanks. Yeah. And another quick question. So you mentioned that metastable states are also stable, right? Is there a well-defined way to store quantum information simultaneously in the ground states and all these metastable states?
Oh, is there a practical way?
Yes. Or not even practical.
Well, so that's what the structure of the memory looks like. Okay, which is like if you look at if you look at any steady state of the problem, it can be written in this form. So this is this hybrid quantum and classical, where this does not depend on alpha. You have some classical index, which is telling you which well you're in, and then this quantum density matrix, which is encoding your quantum information. So formally, that's what it means. This is the structure of the Gibbs state manifold. Practically, I guess I don't even...
maybe practical, what I mean is that I know that time in the ground state as long as there's no violations of stabilizers.
Oh,
Right, so
yeah,
there's like
that part is easy. That part is easy. Just pick in fact, you can pick a typical stabilizer state, okay, decide that I'm going to violate some number of checks. That's a well-defined stabilizer state. As long as it's at a low enough energy density, you can actually prove that with high probability, it's surrounded by a well and disconnected from the ground state. So you'll end up in one of these other wells, and then by acting with the same logical operators that you had for the ground states, you can get to all the other wells there.
Thank you.
Thank Vedika one more time, and then switch gears.